Hey guys, welcome to the first video in my series on the t-distribution. So in this video today, we'll be talking a little bit about the history, about the intuition of the distribution, and then we will be deriving the t-distribution from the t-statistic. So let's go ahead and get started. So about the history, it was first seen in a paper, it was derived by Helmert and Ludroth in 1876, and it was part of a posterior distribution. Okay, so that's the first time basically it's seen in recorded history. The next time it appears in 1895 as Pearson's type 4 distribution. Of course, that's the famous Carl Pearson, who has created the R correlation coefficient that we're all familiar with. So Pearson's R. In 1908, however, is when it appeared in Biometrica, and it was in an article that was written by somebody who used a pseudonym called Student. Okay, so William Gossett was this person who called himself Student when he was writing in scientific articles, and the reasoning is a little unclear. Maybe he didn't want his competitors to see his research. Maybe he just didn't want to be famous. Not sure. Well, I mean, as famous as you can be in statistics, but it ended up being, so let me just talk a little bit about in Biometrica. So William Gossett was using this because he was studying, I think he worked at a brewery, and he was doing studies where he had a normally distributed population, but his samples, he didn't know the population standard deviation, and he often had small sample sizes. Okay, so it led to this t-statistic, which he could then use in inference procedures about the population. All right, so it was popularized by Fisher, of course, another giant in statistics, who called it the student's distribution. Okay, so that's a little bit about the history. Now we come to intuition behind the t-distribution. So if we have some, let me go here. So suppose we've got a population, a random variable X that follows a normal distribution, and then we take random samples, X1 through N, and define the mean in the typical way and define the standard deviation in the typical way. Then what we can do if we want to make inferences about the population, so for example, if we don't, well, if we just, let's just say we want to make inferences about the population, well, then we can use the Z statistic here. All right, so almost everybody's familiar with this who studied statistics at all. And this ratio allows us to standardize the mean in a sense, right? Okay, and this is what Gossett would want to do. However, the case was that the standard deviation was often unknown. Okay, so the next logical thing to do then would be to go ahead and use an estimation of the population standard deviation, which would be the sample standard deviation. Okay, so in the case that we have this random sample that's coming from a normal population, we can use this as a z-score. But in the case that this population standard deviation is unknown, then we can replace that with the sample standard deviation, and we have the t-statistic or the t-score. Okay, so so now we've got this. So we've got this t-statistic, right? And what we would like to do is determine if a random variable has this shape or this expression, then what is its probability density function? And the probability density function can be seen here, where V happens to be our degrees of freedom. Okay, so here's our degrees of freedom. Okay, so this is actually the probability density function. And so that means what? It means that if we integrate this, we can get the probabilities for inference. Okay, so what I want to do in this video is to go ahead and derive this distribution from the z-score. Okay, so then before I do that, we're going to we're going to need a few facts. So let me go through here and we'll look at the facts. Okay, so first of all, let's just take a look at the distribution. What does it look like? So in the case that the degrees of freedom equals 1, you have this distribution here, which is actually just the Cauchy distribution. And then for every other different degrees of freedom, you've got a different distribution shape. Now, notice the scale here is from 0 to 0.2. Okay. Next, we can again, so I just want to make a comparison here between the t distribution when the degrees of freedom is equal to 1. So that's this graph here, and the Cauchy distribution. And you can see that they're precisely the same. Okay, so when the t distribution has degrees of freedom equal to 1, it is in fact simply the Cauchy distribution. All right, so then if we let the degrees of freedom increase without limit, then what happens to the t distribution is that it's asymptotic to the standard normal distribution. So it converges to the standard normal distribution as the degrees of freedom increase without bound. So, okay. And if you have, one thing you'll notice about the t distribution, just in general, not letting the degrees of freedom go to infinity or anything, is that it is bell-shaped. It looks similar to the normal distribution, but it will have wider tails. It'll have some people call them fatter tails at the end. All right, so let's continue then. Now, in order to derive the t distribution, which is what I want to do, I'm going to need some key properties of samples drawn from the normal populations. Then I'm also going to need the gamma distribution PDF. We're going to take a look at that. And then we're going to use a theorem about the PDF of independent joint random variables in our derivation. Okay, so first of all, the properties of samples drawn from normally distributed populations. So if we've got a random sample where it's drawn from a population that's normally distributed, and we define the mean of each sample and the standard deviation of each sample as we showed in a previous slide, then the results are that the mean and the variance of the sample standard of the sample are independent random variables. So x bar and s squared are going to be independent random variables. My x bar is going to also follow a normal distribution with this standard error. And this term here, which is the ratio of my sample variance and my population variance with n-1 here, has a chi-squared distribution with n-1 degrees of freedom. So these are all going to be important in our derivation. The next thing I want to show you is the chi-square distribution. So of course, the chi-square distribution, we use this for goodness of fit test, for a test of independence and so forth. And this is its probability density function. And you can see that inside of it, we have the gamma function. And it's valid for values of x that are greater than 0. Otherwise, it's 0. Okay, so just take a look at it now and pay attention to it, because we will use this in our derivation here. Okay, then we also have the gamma probability density function. And one thing I want to note here is the kernel of the gamma distribution. So if you're looking here, we will use this also in our derivation. Okay, so pay attention closely to this. And again, this is also valid for only positive values of x. Okay, so we're going to use these two pieces of information. Now let's continue on. So the last thing which I mentioned is that, hold on, let me get rid of that, is that we're going to need this fact about independent joint random variables. So if two random variables are independent, then we can find that the product of their probabilities is the intersection. I'm making this, I'm kind of like butchering this, hold on. me write this down because it looks, if you haven't studied probability like beyond high school or something, then you might not know what this looks like, but in all fairness, this really is this. Okay. So if you've studied statistics or anything in high school or college, you've probably seen this. So that's basically what we're saying here. We have two independent random variables. And actually, we can also say this: the probability of A given B is equal to the probability of B, right? So they're independent random variables. And let me clear that. So it means that since they're independent random variables, when I write their joint distribution here, it's equal to the product of their marginal probability distribution. So I can just take it apart and multiply them together. All right, so then that brings me to, let me clear this. Clear all terms. Okay, so that brings me to the next part, which is a bivariate transformation, which I guess I didn't mention that. So we will use a bivariate transformation. So we're going to transform from the product of, so we're gonna take our t statistic, all right, and we're going to turn it into the product of two distributions, the product of two random variables whose distributions we know. All right, and then those two random variables will have distributions that are independent. And because they're independent, we can write down their joint probability density function by writing the product of their individual, or if you like, if they're marginal density functions. And then from that, we'll be able to use this transformation to obtain a probability density function in terms of t, which is what we want to do. So now let me just walk through this. Basically, we want this formula here. So we're going to take this and we're going to transform this into simply f of t. Okay, so here it means we're going to take these two h1 and h2, and then we're going to take the Jacobian to get this value here. So what's the Jacobian? We're going to take the determinant of the matrix of these partial derivatives. And eventually, like I mentioned, the idea is that we're going to be able to get this expression, which is the CDF, and then upon using the fundamental theorem of calculus, we can get the PDF, which is f sub t of t. Okay, so that will be our probability density function for the t distribution. Okay, so I think, yeah, that's going to be it. So now I think what I'm going to do is actually put this in the next video. All right, so that's a lot. And you'll see everything working as we go about. So let me just go back here and summarize this. All right, so we're going to start by looking at our t distribution. We're going to start by looking at our test statistic, our t-score. Okay, and we're going to use properties of samples drawn from normally distributed populations. Namely, we will be using, let's see, we're going to be using the fact that we can get these two random variables, and we're going to be using the fact that X bar has this distribution, and also this term here has chi-squared distribution. And in fact, we'll also use the fact about the z-score having a normal distribution. Okay, the chi-squared distribution, we're going to use that because one of the terms we create will have a chi-square distribution. We're going to use the kernel of the gamma probability density function because at the end of our derivation, we'll see this form appear in our expression. We're going to use the independence of joint random variables to write down a joint random variable that we can transform using this bivariate transformation formula to be able to get this formula, which will be our probability density function. Okay, so that summarizes everything up. Now in the next video, I'll go ahead and carry out the derivation step by step. All right, so I think I'll stop here and we'll start again in the next video.